All right, hello again, ladies and gentlemen. This is Mr. Johnny here with some chemistry, some types of reactions. So the objectives for this video is we want to be able to classify chemical reactions as either redox or ion exchange reactions. So those are the two broad types of reactions. And more specifically, are they synthesis, decomposition, single replacement, or are they double replacement? So before we get started, why don't we take a look at a bunch of reactions, and you guys tell me, are there two reactions that you would say are the same type, that they're the same kind of reaction? I'm not talking about that they use the same elements. I mean, is it the same kind of reaction? Go ahead and pause it and look at it, and I'll cheat and just tell you, yeah, there are some that are the same. So if you take a look at this one and this one, they're kind of the same, aren't they? They both start with two different compounds. And what happens is they do an old switcheroo, right? They both kind of follow that pattern of just switching partners. All right, so we're going to be looking at chemical equations and seeing similarities and differences between the types of reactions. So as I said, there are two major types, two very general categories that we put these things into. They can be redox reactions, in which case, if you were to break down redox, it's really the combination of two words, reduction and oxidation, which you may remember from previous units. So that has to do with the charges on the atoms. So if the charges change, then you have a redox reaction. You have an exchange of electrons. You have one atom losing electrons and another atom gaining them. All right, so the types of reactions that are redox reactions would be synthesis, decomposition, and single replacement. They're all redox reactions. They involve the transfer of electrons. All right, so transfer of electrons. And then we have ion exchange reactions, which the oxidation numbers or charges do not change. They do not change. They just kind of switch partners. So that would be a double replacement reaction and acid-base neutralization. Those would be ion exchange reactions. So taking a look at redox reactions, like I said, how will you know if you have a redox reaction? Well, you can look at the charges. If the charges change from left to right, then you have a transfer of electrons, and therefore it's a redox reaction because you have something being oxidized. Here it's the hydrogen that is oxidized, and you have the fluorine being reduced. So you got both those things occurring, so it's a redox reaction. All right, so remember this little mnemonic, oil rig. So what's that stand for? Well, oxidation is losing electrons, and reduction is gaining electrons. So if you lose electrons, then you become more positive because electrons are negatively charged. They're negative. Whereas if you gain electrons, right, if you're gaining electrons, then you become more negative because you're getting more negative things. You're getting more electrons. So which of the following are redox reactions? Well, in order to do that, you got to figure out what their charges are. I'll do one example with you. Well, hydrogen's in a compound, so is chlorine. So I look up chlorine's charge, it's -1. Hydrogen's got to be +1. Anything that's by itself is a 0, right? I just think of it like losers who sit by themselves are zeros. I can relate, right? So I know the hydrogen over here, even though it says 2, it's still just hydrogen. It's just hydrogen by itself, so it's got a charge of 0. Chlorine still -1. Zinc, I look it up, it's got to be +2. So this is definitely a redox reaction because the charges change, right? H went from +1 to 0, and zinc went from 0 to +2. All right, so TV movie magic, already got the charges done. So the first one we said there was reduction and oxidation. And then this one right here, you look, well, they both start with a charge of 0 and they end up with different charges. So that's a redox reaction as well. Whereas in this example, Li is +1 and then it's still +1 over here. So that didn't change. CO3 is -2, it's still -2. Ag is +1, it's still +1. NO3 is -1, it's still -1. So that is not a redox reaction. All right, so synthesis reactions follow a general form of basically you have two separate things and you combine them to get one bigger thing. So examples would be the oxidation of magnesium. So magnesium burning in oxygen. It's one of my favorite reactions. I'll probably do it in class if I haven't done so already. Gives off a really bright white light and a lot of energy. This would be a synthesis reaction because you can see you start with two different things and you end up with one. All right. This would also be a synthesis reaction because you're combining things to give you one new thing. So here's a clever animation. We got two Mgs and one O2, and it's going to give us two MgOs, right? Whoa, oh my god, crazy. Yep, I know. So decomposition reactions, well, if you know what decomposition is, it's exactly what you would think it would be. You start with one thing and you break it down into different parts. You break it down. So for example, H2O being broken up into H2 and O2 gas. It's the opposite of synthesis. Right? So KClO3, you're breaking it down into KCl and O2. All right, ready for this? Booyah! Look at that. Water being broken down. One more time. Water, H2O, being broken down into H and O's. There you go. All right, single replacement reactions. They're replacing one thing. So you have a compound and you have an element. One of these elements switches. You replace it. Right? So you have one thing being oxidized and one thing being reduced. So if you take a look here, A starts as 0 and it goes to plus. So the thing being oxidized would be A, 0. Thing being reduced, well, what went down in charge? X did. It went from plus to 0. So it went down in charge. So the thing that's being reduced would be X plus. Then what about this Y? This Y minus? It stays the same. So it's a spectator. It didn't react. It just watched the reaction happen. So the spectator ion would be Y minus. So if we take a look at some of these examples, they are also single replacement. You can see iron by itself, it replaces the copper. So now it's the iron with the sulfate and copper by itself. In this example, we got zinc and HCl. Well, the zinc replaces the H, so now it's zinc up with chlorine and hydrogen just by itself. This I call the home wrecker reaction. And I think that's how you spell wrecker. Because it's basically, you know, got a happy couple over here, then iron's like, I don't think so, I'm gonna wreck that home, I'm gonna be with sulfate. And copper's like, what? Now it's all by itself, crying, you know, oh. That's how I think of it. All right. So here's an animation. So we start with zinc and HCl, and they're going to do the old switcheroo with partners, right? Zinc's going to kick out hydrogen, and it's going to couple up with the chlorines. And the hydrogen is going to be left by itself. Then we have ion exchange reactions, which exchange ions. This I call like the square dance, among other things, right? Because you're switching partners, right? You both have a partner, but then you switch partners. So if you take a look, it has a general format of like this: XY paired up, and then AB paired up, and then they switch partners. Instead of X being with Y, X is going to be with B, and A is going to be with Y. When you do the switch, it's important to make sure that you switch the positives or you switch the negatives. They switch up. You can't have X plus A plus together. That doesn't work. All right, so here's some chemical equations. We got Na with Cl and we got Ag with NO3. And now they're going to do the old partner switch. The Na and the Ag plus are going to switch spots and you get new products. All right. The reason these reactions occur is because one of these products is insoluble. It becomes a solid or it changes phase. So if there is no insoluble combination present, then a double replacement won't occur. All right, so let's do a little practice. What kind of reaction is this? I have copper, I have chlorine, and I'm getting CuCl2. Well, hopefully you can realize that that's a synthesis reaction because it follows the general formula of X plus Y, giving us XY, a new compound. All right, so things to watch out for is those Brinkelhoffs, the things that show up in pairs: Br2, the I2, the N2, the Cl2, the H2, the O2, and the F2. All right, so you want to make sure that you don't let them trip you up. So here I have an example of a partially completed equation. I have H2 plus Br2 giving me 2 blank. Well, what goes in here? All right, the best way to do this is create an inventory on both sides so you can figure out what's missing. So I got 2 hydrogens on the left, 2 bromines on the left, and I got 0 and 0. I also got this 2 in front, so whatever I put in this blank is going to get doubled. Well, if I need 2 hydrogens in that blank, I'm going to have to put 1 because that 2 is going to double it. So now I got 2 hydrogens. All right, well, I also need 2 bromines. And if that 2 is in front, I'm just going to have 1 bromine in the equation. Because now I have 2 bromines. So that's what's missing. What kind of reaction is this? I got H2 plus Br2 giving me a new compound. Well, that's just like X plus Y giving me XY. That is going to be a synthesis reaction. Quick review of this stuff using table F. There's a video already on how to do it, but let's take a look at them being applied to double replacement reactions. We got 2 possible products, right? We're mixing these 2 compounds together, and we're going to do the old switcheroo and see if one of those products is insoluble. So I'm going to have to use my table F, and I'm going to look up, CO3. I found CO3. It's insoluble except when combined with group 1. Ions are ammonium. Copper, not an exception, so it is insoluble, which means it's going to be a solid. So hopefully I can check Na and Cl. Well, hey, look, I found Na right here, and it's soluble without any exceptions. So I know that this is going to be soluble. So how do I say something's dissolved in water? Put AQ. All right, so S for solid, AQ for dissolved in water. This reaction will occur because you make a solid product. All right, please bring questions, and I will see you in class.